So we reached the end of Laplace transforms, meaning there's one thing left for us to talk about, and it's the delta function. Now, what's happening with the delta function? First off, you'll notice we didn't say delta function, we said delta function. It's kind of a little bit unusual in that it doesn't fit what we usually think of as a function. So what's going on is that we're going to take everything that we care about and compress it down to just one moment, like the song, one moment in time. And so in particular, the delta function is essentially 0 everywhere except at one point, namely when the input into the delta function is 0, so we'll often do a shift. So delta t minus a says only at t equals a does anything happen. But the other thing is if we integrate over all numbers, we get 1. And so, in other words, you can think of it as there's this super teeny tiny triangle with width 0, but infinite height, so the area is 1. Now, you might be thinking that doesn't sound right. Exactly, which is why we say function. But putting that aside, that it doesn't seem right, we'll just go with it. And so now there's this very simple rule. It says, okay, we know if we integrate just the delta function, we get 1. So if we integrate the delta function times any other function, what comes out? Well, the only place we care about is when the delta function, the input there is 0, which would be at t equals a. Say, all right, well, what happens to this part at a? That's f of a. So it says, okay, so it's like you're scaling your big rectangle by f of a. So the output is f of a, which allows us to say we can take the Laplace transform of the delta function. And this is the integral 0 to infinity, e to the minus st delta t minus a dt. In other words, it's you go back to the definition, right? So we have our input into the Laplace transform, so you put it in the integral. And then I say, well, wait, we know what happens. All we have to say is what's going on at t equals a, and we plug in t equals a, so you get out e to the minus as. And that's it. Now, how do we use the delta function? Well, the delta function is when we have these sort of momentary pulses to our system, or a whack, if you will. So maybe we have a spring moving, and then we hit it with a hammer. Or there's an example here where you can imagine you have a baseball bat, and you hit the ball. Well, you know, that's just at one moment, one pulse. So anytime there's this like one moment pulse reaction, that's when we use the delta function to model that. Now, it will only show up when we're talking about it in terms of differential equations and solving our differential equation. So we're going to have some differential equation equals a function that involves delta. And when we solve, and we'll see this again, when we see deltas in our right-hand side, it's going to lead to u's in our solution. So in particular, we're never going to see deltas at the end. We're only going to see u's. So for the rest of this session, we're just going to do as many problems as we can, doing practice with differential equations, both with delta and with piecewise, just so we make sure we have enough practice, because who doesn't like a good bit of practice? So one quick comment before we jump in. You might be thinking, hey, these piecewise functions, even these delta functions, can you solve those without Laplace transforms? And the answer is yes, as long as you understand. It's a little bit simpler to see with piecewise. So for instance, suppose you had x double prime plus x prime is 1 plus 2ut minus 2. So in other words, we have this function, it's going along, and then it jumps up. So that's the piecewise 1 plus 2ut minus 2. And we have some initial conditions. Now, without Laplace transforms, the process is you first solve it at the initial point, and you go up until the first change in the right-hand side. And then you say, okay, now that I've reached the right-hand side, we figure out what are the situations. What's the values for x and x prime? So essentially, we're ready to prime the pump for the next piece. So now we say, okay, now suppose we start at 2. So we need to get our initial conditions from above, and then we have to update our differential equation, and we solve that differential equation. And then once we have that solution, we're going to glue them together. They will glue, and that's because this step here guarantees that where we end up at the first step is where we start at the third step. And now that's just if we have one change. If we have multiple changes, we'd have to do that for every single piece. What if we were going to do it with Laplace transforms? The answer is, you just do it. And Laplace transform says, I'll work it out for you. Don't worry, life is good. And so, let's do it. So solve for x of t, where x double prime plus x prime is equal to 1 plus 2 u of t minus 2. And initial conditions here, x of 0 equals 1, x prime of 0 is 0. All right, well, here we go. What do you do? We're just going to go through the process, right? We're not going to say this every time, so we'll do it really quickly. Take the Laplace of both sides, manipulate to solve for your capital X, take inverse Laplace, right? Basically, 3 big steps. The middle step being the most important step, also known as algebra. So, we have the Laplace transform of x double prime plus Laplace transform of x prime is equal to Laplace transform of 1 plus 2 Laplace transform u of t minus 2. And of course, you should always make sure, have your equation sheet handy. Now, how do we handle x double prime? There's a formula for that. So this would become s squared capital X minus s x 0 minus x prime 0. For x prime, s capital X minus x of 0. For 1, this is going to become 1 over s. For u t minus 2, well, this is going to become e to the minus 2s, because whenever you see u, it's e to the minus 2s, and that's times the Laplace of 1, which is 1 over s. All right, well, we put in what we know. We have our initial conditions, so x prime is 0, that's 0, that's good, and x of 0 is 1. Great. So let's see what we have here. We have s squared plus s times x, and now these terms here will move across. We have a minus s and a minus 1. And so when we move them across, it will become s plus 1, and then we have plus 1 over s, and here we'll write this as 2 over s e to the minus 2s. So divide. X is equal to, well, we can think of this as s plus 1 over s squared plus s. And we can do this separately. That's okay. Or, of course, we can do them together. It's whatever we feel like. And we'll just go through and think about what's going on. Now, this first term, s plus 1 over s squared plus s. Well, notice that s squared plus s is the same as s times s plus 1. And you can actually divide, and we say, ah, nice! It's 1 over s. Cool, 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 cool. All right, well, that's good. Now, these other two, well, see, look, they're basically the same. They're just a factor of 2 difference. So we only have to do 1. Now, let's focus on this one. Again, you can factor an s out. So this is really, downstairs, s squared times s plus 1. All right, so here we go. Partial fractions. Yes, partial fractions are going to show up a lot, so we're going to get comfortable. At least we're going to try. So 1 over s squared times s plus 1. Well, we have s squared, s plus 1. A, B, c. All right, clear the denominator. Use this left-hand side, the original denominator, to help you remember. So in case you're like, wait, what do I multiply by? Whatever you started with, that's what you multiply by. And that leads us to 1 is equal to, well, the first term, we'll get an a. We'll get a single s, because only one s canceled, s plus 1. Then plus b, s plus 1, plus c, s squared. All right, good, 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 good. Now, time for us to make good choices. Well, 0, that seems pretty good. Plug in s equals 0. You get 1 is equal to a times 0 plus b times 1 plus c times 0. Okay, so b equals 1. Negative 1. Okay, 1 equals a times 0 plus b times 0 plus c times 1. Great. Now, at this point, you're like, well, 0 is a good choice and negative 1 is a good choice. We're out of good choices. So what do we do? We can do a couple things. 1, we can just plug in a different number. 2, we can look at coefficients. I like to just keep plugging in numbers because I like plugging numbers in. So plug in positive 1. You know, the two favorite numbers of mathematicians, 0 and 1. All right, so we'll get 1 equals a times 1 times 2, 2a, and then plus b, but we know what b is, that's 1, so plus 2, and then we're going to get c, which is 1 times 1, so plus 1. Well, you'll see that's the same as 2a is equal to minus 2, or a equals minus 1. All right, so what do we have here? Well, we now have the following. The first term we had was 1 over s. Okay, that's from this piece right here. Then we did partial fractions, and when we did our partial fractions, we saw that we got the following. We had a was a minus 1 over s, b was a 1, so plus 1 over s squared, and then c was a 1 over s plus 1. Now here, it's the same thing. We'll just factor 2 out. 2, then we have a minus 1 over s plus 1 over s squared plus 1 over s plus 1 e to the minus 2s. And at this point, we're like, ooh. Our preps are like, oh, we're somewhere in that range, right? Because cancellation. All right, good. Now, are we ready to take Laplace transforms, and why? Because everything's good to go. We're actually in a pretty good place here. So we're now ready to work it through. So our final answer. All right, let's see if we can squeeze it in here. Little x, inverse Laplace of capital X is, well, we're going to do the inverse Laplace of 1 over s squared plus 1 over s plus 1. And we'll do that. And then we're going to add 2 inverse Laplace. And I'm going to put the e to the minus 2s at the start just to help us remind ourselves what's going on. All right. Now, we'll start with the first part. 1 over s squared becomes t. All right. So we have t. 1 over s plus 1. Now, 1 over s plus 1 is 1 over s minus 1. So that will become e to the minus t. And then we have plus 2. This e to the minus 2s tells us we're going to do u t minus 2. Right? So whenever we see an e to the minus as, u of t minus a. Now, normally, what would we have? Well, this would become this part right here, without the e to the minus 2s, would become minus 1 plus t plus e to the minus t. So what is it going to become now? Well, it's going to become that thing, except instead of t minus 2. So minus 1 plus t minus 2 plus e to the minus t minus 2. And that's it. We're done. And you might say, well, wait, shouldn't it have been piecewise? It is, right there. That's the u of t minus 2. That handles the piecewise. And isn't that a lovely answer? I think it is. And it works out very nicely. All right. Well, good. Look at us, solving problems. We're problem solvers. So for our next problem, a mass of 1 on a spring with constant k equals 4 starts with x of 0 equals 3 and x prime of 0 equals 0. At time 2 pi, the mass is hit with a hammer, whack, providing an impulse force of 8. In particular, they gave us the equation. X double prime plus 4x equals 8 delta t minus 2 pi. So this impulse force, that's delta. So if you ever see the word impulse or pulse or hit, that means it's just an instantaneous thing. That's delta. It's when something is sustained, that's an on-off, that's U. And that's an external force. The spring constant is showing up here. So we like spring problems. They show up a lot in this part of the course. So I hope you're ready to spring back into action, as it were. All right, and we're going to solve for x of t. Don't forget that even though they gave us a differential equation, they also gave us these initial conditions, which are going to come into play. So here we go. We've got everything we need. So we start. And again, 3 steps. Take Laplace transform, do algebra, take inverse Laplace. So we're going to have Laplace of x double prime plus 4 Laplace x is equal to 8 Laplace delta t minus 2 pi. All right. Well, now we apply our rules. And so we have that Laplace transform of x double prime will become s squared x minus s x 0 minus x prime 0. Okay, that's the first part. Plus 4x equals 8. And the delta is just exponential, nothing else but exponential, e to the minus 2 pi s. All right, good. Well, plug in what we know. We know x prime, we know x 0. So we have that the x prime, that's 0, and the x of 0, that's 3. And so we have the following. We have s squared plus 4x. We'll move the 3 across to the other side. That's equal to 3 plus 8 e to the minus, whoops, I said 3s. Yeah, this is the biggest challenge. It's just copying, making sure you copy everything down right. So it's all right, take your time. We're good. So that says that capital X is equal to 3s over s squared plus 4 plus 8 over s squared plus 4 e to the minus 2 pi s. Now, preparing ourselves for what's about to happen, we are in our mindset, we're getting ready for inverse Laplace. We're almost there, but we'll just do a little bit of cleanup. Now, for the first term, we won't do much. We'll bring the 3 out. So this is s over s squared, and for 4, we'll think of it as 2 squared. Now, for the second term, we're going to have an s squared plus 2 squared. The constant upstairs, and notice it is a constant, there's no s, is currently 8. What would we like it to be? Well, to fit our formula sheet, we see that there's a formula that says b over s squared plus b squared. So we'd like it to be 2. So if we'd like it to be 2, we make it 2. Isn't that great? If you want it to be something, you make it something, but then adjust. Okay, so our adjustment, well, we had 8, here's 2, so we'll put a 4. That's great. And this e to the minus 2 pi s, that's great to keep there. All right, now we're ready to do our last step, which is the inverse Laplace. And I know you're thinking like, we just started this problem. Yeah, that's how fast they can go. You know, they grow up so quickly. All right, so our x, that's the inverse Laplace of capital X. So this would be 3 inverse Laplace of s over s squared plus 2 squared. And then plus 4 inverse Laplace of 2 over s squared plus 2 squared e to the minus 2 pi s. All right, well, what's going on? So for the first term, that's not too surprising. That's straight from our formula sheet. We say that's a cosine, cosine 2t. All right, now for the next term, well, we have an e to the minus 2 pi s. So this e to the minus 2 pi s is telling us that essentially there's a shift going on. There's an on-off happening, and where is it happening? It's happening at 2 pi. And so we're going to have, whoops, sorry about that. We're going to have u t minus 2 pi. Now, this portion, this 2 over s squared plus 2 squared, we say, what would it be if we didn't have to worry about the e to the minus 2 pi s? And it would be a sine, sine 2t. So we say, great, it's still sine. So it's sine of 2, but here you replace t by t minus 2 pi. And there we go. All right, great. Well, we can clean it up a little bit. So that's 3 cosine of 2t. And then, well, notice this is this inside the sine. This is 2t minus 4 pi. But sine is periodic. It repeats every 2 pi, so it also repeats every 4 pi. So this becomes plus 4 u t minus 2 pi, and then it's sine of 2t. And there we go. That's our answer. Life is good. And all right, well, that's cool. Now, a couple of things to note. This delta t minus 2 pi that was in our original function became a u of t minus 2 pi in our answer. Is that coincidence? No. Where you see a delta, it's going to become u. And so, all right, it just happened to work out that way. You can also graph this, and it's, but we're not asked to graph this. And but it turns out that it has initially an amplitude of 3. See, that's the 3 cosine 2t. Then after your pulse hit it, it goes up to an amplitude of 5. And so this time when the hammer hit, it actually caused things to get bigger. Now, that's not always the case. Sometimes it causes things to get smaller. It just depends. But that's our problem. We're ready for more. Now, you probably thought when you heard we're ready for more, you were probably like, oh, okay. You weren't expecting an infinite sum. But that's okay. Let's talk about this. A large group of people marched at a regular pace when crossing a bridge. So they were marching in uniform, so to speak. And the vibration of the bridge can be modeled by the following equation. So you have y double prime plus 9y. So in other words, the bridge can move up and down. So it's acting like a spring. And the people marching are stepping on it at a very uniform pace. So what you see here is when you see this sum, each time you step, that's a pulse, and it's coming in at regular intervals. Initially, the bridge was just relaxed. It was calm. Nothing was happening to it. Well, what's going to happen? All right. So y of t is the vertical displacement, and solve the initial value problem using the method of Laplace transform. As soon as you see delta, it's like you're doing Laplace. There's just like no way that you're not doing Laplace. It's just so much simpler and easier to follow. So we're going to do it. Now, what do we have? Well, we do our process. Laplace transform y double prime plus 9 Laplace transform of y. And of course, we're not concerned that this is using y's when we've done so much with x's. It's a letter. It's a symbol. Symbols can change. The math doesn't. Now, the nice thing is Laplace transforms are linear. So we can pass it through the sum. So this is the sum, k equals 1 to infinity, of the Laplace transform of delta t minus 2 pi k. All right, great. Well, now what do we have? Well, we have s squared capital Y minus s y 0 minus y prime 0 plus 9 capital Y is equal to the sum, k equals 1 to infinity, of e to the minus 2 pi k s. All right, don't try to simplify this. We'll just leave it here. In other words, don't be like, aha, I'm going to write this sum and use that. I know what a sum is, you know. It's a geometric series, and no, leave it like this. It's going to be easier for us for what's about to happen. Now, what do we see? Well, y of 0 is 0, y prime of 0 is 0. So that makes it really easy. There's nothing to move across. And on the left-hand side, we say, well, really, this part right here, this is s squared plus 9y. Okay, so to solve for y, we'll divide. So we divide everything by s squared plus 9. So we now have that y, this displacement, is the sum, k equals 1 to infinity, of 1 over s squared plus 9 e to the minus 2 pi k s. And are we ready to do our inverse Laplace transform? Yes, we are. You're like, what? What? Already? Yeah, isn't it great? Problems don't have to be long, and we enjoy it when they work out, right? So inverse Laplace of our sum. Now, the nice thing is the inverse Laplace is also linear. So this is the sum, 1 to infinity, inverse Laplace of 1 over s squared plus 9 e to the minus 2 pi k s. All right, good. Now, what do we have? Well, we have our sum. And we have an e to the minus 2 pi ks. What is that doing? Well, when we see that, that means we're having on-off happening. So we're going to have u of t minus 2 pi k, right? We grab the coefficient of s, minus 2 pi k, so 2 pi k is a, t minus a. Now, s squared plus 9. Oh, we did forget one thing. That's okay, we can fix it really quick. What should we have here? Well, s squared plus 9, we should have, this is s squared plus 3 squared. So we should have a 3 upstairs, so we'll put a 1/3 out in front. All right, great, no worries. 1/3, and now this is a sign. we see the sign, and it's sine of 3t. Now, that would be if we only saw that. But because we have the shift, it's not going to be 3t, it's going to be 3t minus 2 pi k. All right. Well, can we clean this up? Yes. And there's something coming which is going to be really cool here. So hold on. We have, this is 3t minus 6 pi k. But sine is periodic, right? And so if we've gone around 6 pi k times, we're back where we started. So we can drop that. All right. So what we end up with is 1/3 the sum k equals 1 to infinity of u t minus 2 pi k sine of 3t. All right. Good. Done. Okay. Well, is that the whole story? There's a little bit more. And but as far as the problem goes, this is correct. We have the solution. And but what's happening here? Okay, so you can imagine we have a bridge, and we have our people crossing it. Look, we're crossing the bridge. And now, so forth and so on. And well, what's the key? When we look at this function, what's happening to it? Well, as we look at this function, we say initially it behaves like 0. Okay, so this behaves in the following way. It's 0. Where do we have space? We'll try to put it into here. It's 0 up until when? When's the first time something happens? Up until 2 pi. So initially that says, okay, nobody's on the bridge. Then at 2 pi, we have our first step. And so we add a sine 3t. So don't forget the 1/3. So then it's 1/3 sine 3t. And that's for the next little bit, until the next step, which will happen at 4 pi. Then what happens? We add another sine 3t. So then it becomes 2/3 sine 3t. And that's going to hold true until the next step. And then what's going to happen? We're going to add another sine 3t. And so we're going to get up to 3/3 sine 3t. And okay, I'm running out of space, so we're going to have to tell the punchline. What's happening? Well, what's happening is as time goes forward, we're stacking these sines on top of each other. So after a very long time, what that means is that where the bridge was initially at rest, then it vibrated a little, then it vibrated more, then it vibrated more, and then it's going to vibrate more, and then it's going to eventually go crazy out of control. The bridge will collapse, and it will break. And this actually happens. And so it can be the case that when people walk across the bridge, if they're walking in uniform and they walk at just the right pace, then what will happen is the vibrations will build off of each other. That's what's going on here. And the bridge will collapse. So that's when armies, when they march, they'll march until they get to a bridge. Then they'll sort of shuffle along at some sort of randomness. And so they don't want to have this behavior after they cross the bridge back into formation, back into marching. And so this shows you, hey, math explains why marching in uniform across a bridge can be bad. And so, all right, there we go. So that's the story. All right, well, we still have lots of time. More problems. Whoa, an essay problem. No, we're not going to panic. A full 30-gallon tank is being used to make soup broth. For this tank, 10 gallons per minute of pure water is constantly coming in, and 10 gallons per minute of well-mixed broth is constantly going out. Now, initially, at time 0, there's no seasoning in the tank. At time t equals 1, 12 ounces of seasoning are added to the tank. At time t equals 5, 20 ounces of seasoning are added to the tank. And at time t equals 10, 6 ounces of seasoning are added to the tank. So, if x of t is the amount of seasoning in ounces in the tank at time t, set up and solve a differential equation for x of t. Wow! A tank problem! It's been a while since we've done one of these. This will be fun. Okay, so we know a couple of things. We know our initial conditions. Let's just get that out of the way because we see initially no seasoning. All right, so the good news is we know x of 0. X of 0 equals 0. Nice. All right, well, what else can we say? Well, what is x prime? Now, x prime, that's our in minus our out. Let's talk about our out first, because that's the one that we usually get stuck on. We see that we have, it's a 30-gallon tank, and 10 gallons per minute is coming in, and 10 gallons per minute is going out. And so, well, that says 10 over 30, that's 1/3 is leaving. So you say, okay, so our out, we can think of it as minus, and if you think about it as flow times concentration, you know, as 10x over 30, or you can just think of it as like, well, 1/3 of everything's leaving, so 1/3 of the seasoning's leaving. So, okay, so there's our out. What else do we need? We need our in. Okay. Well, how much is coming in? Well, we're told that 10 gallons of pure water comes in at every moment. Pure water, there's no seasoning in that. So where's the seasoning coming from? Well, that's coming from this second paragraph. And it says, okay, at time t equals 1, 12 ounces of seasoning are added to the tank. What does that mean? Well, that's sort of like, you can just imagine there's somebody standing over the tank and goes, doop, and just at time, doop. So it's not this sustained on-off type thing. It's a boom, a pulse of seasoning. So what describes that? Delta. All right, so we say, okay, so at time t equals 1, there's 12. So what we say is, okay, so we're going to have 12, and then we have to say when it happened. That's going to be our delta, just then t minus 1 time 1. All right, time t equals 5, there's 20. Okay, so that's 20 delta t minus 5. And at time t equals 10, there's 6. All right, 6 delta t minus 10. All right, and that's it. We're ready. We're good to go. I hope we're good to go. So not much really to do other than move that across. So you have x prime plus 1/3 x equals our 12 delta t minus 1 plus 20 delta t minus 5 plus 6 delta, that's a terrible looking delta, t minus 10. All right, and we take the Laplace of everything. So the Laplace of x prime plus the Laplace of 1/3 x is equal to 12 Laplace of delta t minus 1 plus 20 Laplace of delta of t minus 5. You know, I just realized it's kind of remember how to write Laplace and deltas. They're so similar to each other that my muscle memory is trying to kick in and write one when I'm trying to write the other. So, well, take your time. We don't give bonus points for being fast. We give points for being correct. All right, well, let's see what we have. Now, here we're going to get our S x minus our x0. But we know x0 is 0. So that's great. Then we're going to get plus 1/3 x. All right. Then we'll get 12. And then here we'll get e to the minus s plus 20 e to the minus 5s and plus 6 e to the minus 10s. And we say, well, notice this is s plus 1/3 times x, and so you factor the x out, divide by s plus 1/3. So we get that x is equal to 12, 1 over s plus 1/3 e to the minus s plus 20, 1 over s plus 1/3, and that's e to the minus 5s, and plus 6, 1 over s plus 1/3 e to the minus 10s. All right. Okay. Well, what's left? Well, we take the inverse Laplace. Okay. So we have little x, inverse Laplace of big X. All right. Now, we'll just do it. All right? Just for running out of space, so we'll be careful here. So we have the 12. The e to the minus s says u of t minus 1. We expect a u of t minus 1 because we saw a delta t minus 1. Now, what's the function? Well, s plus 1/3. That's s minus 1/3. So this is going to be e to the minus 1/3 times t minus 1. Okay, then the next term, plus 20. E to the minus 5s, u t minus 5. Then here, it's e to the minus 1/3 t, but, of course, we have the shift, so it's e to the minus 1/3 t minus 5, plus 6, u of t minus 10. And then e to the minus 1/3 t again, but, of course, we replace t by t minus 10, minus 1/3 t minus 10. And we're done. That's it. So, again, the deltas become u's. So we expected several u's. We got several u's. And that's wonderful. Life is good. And see how we don't have to be like, oh, many parts, we're going to have to worry about things. Nope, it just took care of it all automatically. Life is good when the math does the work for you. So let's do another example. Here we have a mass of 1 on a spring with constant k equals 4, starts with x of 0 is 0, and x prime is 0 equals 0. And an external force acting, which is cosine 2t. Now, it doesn't keep acting. It only goes for a little bit, from time 0 to 2 pi. And after time 2 pi, the force is turned off. So the spring is initially at rest, which would mean that normally it would stay at rest. But then something is acting on it, then the thing acting on it is going to turn off, and then the spring is going to do something. All right, well, let's see what happens. Now, we want to solve for x of t. What are we missing? They didn't give us a differential equation. Okay, so we got to do it this time. We got to make it. So we know for springs we have mx double prime plus cx prime plus kx equals f of t. So f of t is external force, k spring constant, c damping constant, and mass. Now they didn't talk at all about damping, but we do have a mass of 1 and a spring constant of 4. So this becomes x double prime plus 4x. Now our external force, it starts as cosine 2t. So we say, great, that's cosine 2t. Then there's a change in behavior. So change in behavior, piecewise, we got to do some on-off action. And so we're going to add a on-off switch that occurs at 2 pi. And what do? Well, we're going to turn off the external force. So after 2 pi, there's nothing. And then we're turning off the cosine 2t. All right. Now, we've got to do a little bit of work just to make sure we're good to go. Because we haven't done a u in a while, let's talk about what needs to happen. We want to have this t look like t minus 2 pi. So we're going to just make some notes here. Cosine 2 t minus 2 pi, but then we're going to have to account for that. So that's like minus 4 pi, so you have to add 4 pi. Yes? So now we have our t minus 2 pi. Well, how do we account for the 4 pi? Well, we use the fact cosine is periodic. Say, so this is the same as cosine 2 t minus 2 pi. And we're like, whew, dodged a bullet. Good. All right, so updating. We can now say we have x double prime plus 4x is cosine 2t. And now we're going to have a minus u t minus 2 pi cosine 2 t minus 2 pi. All right, so what happens? Well, we're ready to take the Laplace transform. We've set up our differential equation. We did some work to make sure it was ready to take Laplace transform, and so we take Laplace transform. All right, so Laplace transform x double prime plus 4 Laplace transform x is Laplace transform of cosine 2t minus the Laplace transform of u t minus 2 pi cosine 2 t minus 2 pi. All right, well, term by term, what happens? Using our rules, s squared. Then we're going to get x minus s x0 minus x prime 0. Okay, that's our Laplace of x double prime. Plus 4x equals Laplace transform of cosine 2t. Well, that's going to become s over s squared plus 2 squared. Now, our Laplace transform u of t minus 2 pi cosine 2 times t minus 2 pi. So this part, u of t minus 2 pi, tells us we're going to have e to the minus 2 pi s. This other part, we say, okay, now imagine that the t minus 2 pi was just t, so it's cosine t. We're like, cosine 2t, we know how to do that. It's right there. So that's s over s squared plus 2 squared. Like, great, cool. Now, let's keep cleaning this up. We can do a few things. We know x of 0 and x prime is 0. So x of 0 is 0, x prime of 0 is 0, so those are gone. So what ends up happening is on the left side, we really have s squared plus 4 capital X. Okay, now divide through. And what do we get? Well, that tells us that we have capital X is equal to, and by the way, s squared plus 4, this is the same as 2 squared. So s squared plus 2 squared. All right, so this will be s over s squared plus 2 squared squared. And then minus e to the minus 2 pi s, s over s squared plus 2 squared squared. Okay. Well, what's going on? Should we do partial fractions? The answer is no. It won't do anything for you. And they're like, well, okay, so then we're not going to do that. yeah, you're not going to do partial fractions. It's not going to help. So you say, okay, well, if partial fractions doesn't help, is this on our formula sheet? Okay, so we start looking through and saying, all right, have we seen anything like this before? Is there anything that looks like this that we can use? Yes, there is. Okay, so, because, I'll just write down one of the things is t sine bt. Now, this is something we talked about a few lectures back, and how you said, oh, start with the sine bt, take a derivative, and when you do that, what you end up with is 2 times b times s over s squared plus b squared squared. So we're pretty close. We have the s squared plus b squared squared. We have the s. What are we missing? Well, we're missing 2b. Or is it not 2b? No, we're definitely missing it. Okay, so how do we fix it? Well, okay, in our case, b is 2. So 2b is 4. So we need to have a 4 upstairs. And so we say, great, throw it in. And now we say, well, compensate. And we'll say, hey, this one also. Say, great, compensate again. And now we're ready to do inverse Laplace. Already? Yes! Isn't this great? Don't you just love it when an inverse Laplace comes together? Okay, let's see. Maybe we'll do it down here. So we have little x is the inverse Laplace of big X. Okay, so term by term. Here we're going to get a 1/4. Now here we were just right. So this becomes a t sine of 2t. All right? See that? Now we have s squared plus 2 squared squared, 2 times 2 times s, so that's t sine 2s. Or sorry, t sine 2t. Great. Now, minus 1/4. The e to the minus 2 pi s tells us we're going to have a u of t minus 2 pi. Right? So whenever you see e to the minus 2 pi s, it's on-off switch happening. And then we say, oh, it's the same thing we just did. Just replace t. Everywhere you see t becomes t minus 2 pi. So t minus 2 pi sine 2 t minus 2 pi. All right, we're going to do the same thing we've done several times today already, meaning you're going to be like, all right, he's going to tell us that in the inside of this. Yeah, exactly, that's what we're doing, because there's a punchline here. I want to go through it. So this is 2t minus 4 pi, and then, well, really, that says this is the same as sine of 2t. Okay. So let's write down x. Well, you can say, that is x, Steve. Cool. Let's write down x as a piecewise function. Oh, okay. I see where you're going with this. So when we think of x as a piecewise function, what's happening here? Well, there's two pieces. There's the before 2 pi, before you turn off the external force, and after the external force. So before you turn off the external force, in other words, before 2 pi, you only see this piece. So it starts off as 1/4 t sine 2t. And that's between 0 and 2 pi. After 2 pi, this switch is turned on. So then it becomes 1/4 t sine 2t. So you still have this subtract 1/4 t minus 2 pi, and then sine 2t. And that's for t greater than 2 pi. All right? Well, does this clean up? And the answer is yes, because, I think it's really pretty here. If you distribute through you'll get a t sine 2t times a fourth. Here's t sine 2t times a fourth. The minus means they cancel. So we end up with the following piecewise function. It's 1/4 t sine of 2t up to 2 pi. And then these parts cancel, so what's left? Well, the minus 1/4 times minus 2 pi will get us pi over 2 and sine of 2t. And that's for t greater than 2 pi. That's it. So what's the picture of what's going on here? Well, what's going on is that initially you're growing at a rate, the amplitude is growing. So let's see, we're going to go 2 pi. So we have, all right, that's 1, grows something like this. And then at 2 pi, it turns off, and the amplitude stays fixed. So this is at pi halves up here, and minus pi halves down here. And so from then on, it just oscillates in between those two. So that's the behavior of the spring. That's what we can figure out. And so it's actually a surprisingly beautiful answer. And I like this problem, but I like many problems. You know, it's okay to like a lot of problems. Well, one more? Yeah, let's just do it. One more. Ooh, that looks long, but let's go for it. We're given y of 0 equals 2, y prime of 0 equals 4, and we're asked to solve the following. Y double prime minus 2y prime. Then we have an on-off switch, u of t minus 1, and 4 cosine 2t minus 1 minus 4 sine 2t minus 1. Oh, that was very nice of them. They already wrote everything in terms of t minus 1, meaning we can go right into taking our Laplace transform. Okay, so that's what we're going to do. We're going to go right into it. All right, so we have Laplace transform y double prime minus 2 Laplace transform y prime is equal to Laplace transform of u t minus 1 times 4 cosine 2 t minus 1 minus 4 sine 2 t minus 1. Okay, well, term by term, what happens? Well, for y double prime, we're going to get s squared y minus sy 0 minus y prime 0. Okay, that's the first part. Minus 2. Don't forget parentheses. It's exactly in situations like this that you don't want to forget your parentheses. We're going to get sy minus s0 equals. Now, when we see that u of t minus 1, that tells us we're going to have e to the minus s. All right, this minus 1 tells us minus s. And then we say, imagine that these t minus 1s were just t's. We're like, we can definitely imagine that. And, well, what would we have? The 4 cosine of 2t would be s over s squared plus 2 squared. And then minus 4 sine of 2t would be 2 over s squared plus 2 squared. All right, good. Well, so we've already finished our first step. We're a third of the way done, right? Because there's 3 big parts. Take Laplace, algebra, inverse Laplace. Well, okay, cleaning up. We actually have numbers here. So we ought to be careful. There's a 2, there's a 4, there's a 2. And let's see, what can we do here? Oh, there's some good news here. So what do we see? let's do the y's. We have an s squared y and a minus 2sy. So we put them together and we get s squared minus 2s times y. Great. That's good. How about for the s's? Well, we have a minus 2s. Let's go ahead and just, well, we'll do it in slow motion. Minus 2s. Here we'll have minus 4. Minus 2 times minus 2 plus 4. Nice. All right, on the other side, well, we can certainly put things together. We can write this as e to the minus s, and then we can have 4 times s minus 2 over s squared plus 2 squared. Okay. All right. Well, okay, so the 4's cancel. We'll put the s across. So we have s squared minus 2s y is equal to 2s plus e to the minus s, and then 4s minus 2 over s squared plus 2 squared. And we're almost ready to solve for y. We just need to divide by s squared minus 2s, which, by the way, this s squared minus 2s, this is the same as s times s minus 2. And you'll be like, oh, there's an s minus 2 there, and there's an s there. It's almost as if someone planned it. Because they did. I know. I was the one who planned it. Okay, all right. Anyways, sorry. Back to our problem. We get then that y. All right, we'll do this again in slow motion, but we're anticipating already. E to the minus s, 4s minus 2. We have our s squared plus 2 squared, s minus 2. And we do our cancellation that we already said would happen. We say, well, that's nice, and that's good. And so we're already happy with the first term, and that's good to go. We are going to need to do some partial fractions, but that's okay. That's part of the joy of Laplace transforms. I don't want to say that's part of the misery. No, it's part of the joy. Who doesn't love a good partial fractions problem in the morning? All right, so we have 4 over s times s squared plus 4. We're going to write this as a over s plus bs plus c over s squared plus 4. Clear your denominators. And by that, we mean multiply by s times s squared plus 4. Okay, so when we do that, carry that computation out, what are we going to have? Well, we're going to have that 4 is equal to a times s squared plus 4 plus bs plus c times s. All right. Well, I almost always make good choices. Let's go ahead and for once we'll do coefficients. Why not? Okay, so how about s squared? What do we have? Well, there's an s squared here, and then s times s will be an s squared. So that's a plus b s squared. How about for just s? There's only one place. And that's c times s. What about for constant? Well, there's only one. For a. Now, we say, okay, time for us to do our matching. So we see such things such as, well, 4a has to be 4. C, there's no s, so c has to be 0. And a plus b has to be 0. So what does that tell us? Well, it tells us a equals 1, right? 4a equals 4. B is minus 1. And c is 0. All right. And so we get the following. Okay, so we are now going to update our y. Y is 2 right, because we have that 2 there. Then 1 over s minus 2 plus e to the minus s times, so all of this part right here, that's that partial fraction we just carried out. So that's going to become a over s, well, a is 1, so 1 over s plus bs plus c. B is minus 1, c is 0. So actually, instead of plus, we'll put a minus, and then s over s squared plus 4. All right, good. Now, are we ready to do the inverse Laplace? Yeah, we are. Everything's actually really nicely set up for us. And so we say, okay, that tells us that what we're after, because we're trying to solve, little y, inverse Laplace, capital Y, well, that's 2, inverse Laplace, 1 over s minus 2, plus the inverse Laplace of e to the minus s, 1 over s minus s over s squared plus 4, which we'll write as 2 squared. All right. Well, what do we have? We have 2, and then here, this is exponential function, e to the 2t. E to the minus s, on-off switch, so we're going to get a u t minus 1. We're not surprised, right? Whenever we have a u or a delta, we're going to expect a u or a delta, right? Something happened, so there has to be a different happening. Something has to turn on and off for the solution. If something turned on and off for the problem, something turns on and off for the solution. Now, be careful. Of course, we're always careful. But what do we get? Well, 1 over s, by itself, this would go to 1, subtract, and s over s squared plus 4 is cosine 2t. So we say, okay, now that would be if there wasn't that e to the minus s. But since there is that e to the minus s, we are going to put, instead of 1, we're going to put 1. Oh yeah, actually there's not much to do there because there's no t. But then we're going to have a cosine of 2t minus 1. And we're done. That's the answer. Wow. All right. That one wasn't so bad. Indeed, none of them are bad. It's just practicing, knowing your Laplace transforms, using your table, carrying out the algebra, cleaning it up, doing some partial fractions, carrying out the inverse Laplace, making sure you know your rules for handling the exponentials. All right, well, what a fun ride we've had with Laplace transforms. There's still a little bit of our journey left, but I hope you've been enjoying it so far, and I hope to see you again. Bye.